So today's lesson is going to involve us exploring some concepts we've seen before and also learning about some new ones. So from grade 11 chemistry, you'll remember that we talked about pH. And in fact, even in grade 10, we started to introduce the idea of pH in acids and bases. But in grade 11, we quantified that and we reminded you that we can calculate the pH by taking the negative log value of our hydronium ion concentration. And so now that you guys know what logarithms are, you know that this is a base 10 function and that we can rearrange this formula so that we can solve for pH. So our hydronium ion concentration is going to be equal to 10 to the negative pH. So let's just do a couple of quick calculations to refamiliarize ourselves mostly with just inputting the data into our calculator. So I'm going to ask you to just take a minute, pause the video, and calculate the pH of pure water at 25 degrees Celsius. I'm hoping you were able to guide what you already know about acids and bases and neutral solutions to help you sort of know what it is to expect here. But I know that first of all, the concentration of hydronium ions at 25 degrees Celsius is 1.0 times 10 to the negative 7 moles per liter. And so that is going to be my value that I substitute into the pH formula above. And so my pH in this case is going to be equal to the negative log of 1.0 times 10 to the negative 7, which will give me a value of 7. Not wholly unexpected. Let's try another example. So in this second example, we're asking you to determine the hydrogen ion or hydronium ion concentration of a substance with a pH of 3.2. And for our purposes in these questions, whenever we see hydrogen ion concentration, we're going to interpret that to mean hydronium ion concentration. So in essence, we're going to consider those interchangeable in our calculations. Okay. So when I look at this, I know that I am given my pH value of 3.2. And so my unknown is my hydronium or hydrogen ion concentration, and that's going to be equal to 10 to the negative pH. So 10 to the negative 3.2 is a value I'm going to need to calculate using my 10 to the x button, most likely. Is actually to use the Y to the X button, but that's, whatever you feel comfortable with and whatever is enabling you to get the correct value. So I am getting I'm going to round this to 2 sig fig, 6.3 times 10 to the negative 4, and that is in moles per liter. Okay, so hopefully you managed okay with that. So we've covered pH, but we still have to cover this thing called pOH. And so I'm hoping you already have some ideas that have percolated and you'll know kind of where we're going to go with this. So there's an analogous pOH that describes, instead of describing the hydronium ion concentration, it's describing the hydroxide ion concentration. And so here we see, very similar structural kind of setup to our pH formulas, except that instead these will enable us to calculate our hydroxide ion concentration for our pOH. Let's see how this kind of plays out. But before we do that, I want to take you through a particular derivation for a formula that we're going to use in this section that can be fairly useful. Let's take a look. So what we're going to do in this section is essentially develop a formula that's going to allow us to relate pH and pOH in a simple way. But what we're going to do is we're going to develop it, we're going to derive it. And the reason I think it's important for you to see this is because if you're planning at the post-secondary level to take either chemistry or physics or a quantitative science, then chances are you're either going to have to derive formulas yourself, or you're going to have to be able to kind of work through and understand a particular derivation. Okay, so first off, I'm going to start you off with the first line of my derivation, where I'm essentially just creating, a situation where I have expressions that are equivalent to each other. So I know that Kw is the equilibrium constant that we use for water. It's the water ionization constant. And so when I look at that, I know that that's equal to the product of my hydrogen/hydronium ion concentration and that of my hydroxide. And I know if I'm talking about 25 degrees Celsius, then that value is going to be equivalent to 1.0 times 10 to the negative 14. And so if you've forgotten that, circle back to look at my previous screencast on Kw, water, and equilibrium. So I'm just setting us up here. And so in this next step, what I'm going to do is I'm going to substitute in for, instead of hydronium or hydrogen, I'm going to substitute in a mathematical expression that's equivalent to it. So I know that I can calculate the hydrogen ion concentration by taking 10 to the negative pH. And I can do the same thing with the analogous formula for pOH. And all of that's still going to be equal to 1.0 times 10 to the negative 14. Okay, let's carry on. So what I'm going to do is I'm going to take the logarithm of both sides. So just going ahead, whatever I do to one side, doing to the other side, taking the log of both of those values. So in math, you will hopefully have learned that when I have log of AB, that is equal to the log of A plus the log of B. And so that's all I've done in this step, is just use that principle to separate out those logs based on that particular part of math that you hopefully have learned. Okay, let's take a look at the next step. Now remember, these are all logs with a base of 10. And so you'll remember that if you take the log of power of 10 when it's the log of base 10, then you get whatever is in the exponent. Okay, so log base 10 of 10 is going to give me negative pH. And the same thing goes for this second part of the left-hand side of this equation. Okay, log with a base 10, taking the log of 10 of that, I'm going to get whatever's in my exponent. And so what I get on the left-hand side as a result is negative pH plus negative pOH is going to give me negative 14, because of course I've applied that same principle over here on the right-hand side. So let's get rid of all those negatives. Multiplying my left and my right-hand side of this equation by -1 leaves me with this beautiful, simple formula. pH plus pOH equals 14. At the end of the day, this formula is what you need to know. All this other stuff is just, for interest's sake, FYI. But this is the formula we need to know. And I'm wondering if there's anything about this that seems familiar. Hopefully what you're thinking about is the fact that our wonderful pH scale is a scale that goes from 0 to 14, where our acids have pHs that are below 7, and our alkaline solutions, or our basic solutions, have pHs that are above 7, and solutions around 7 are considered neutral. So you may have wondered in the past, well, why is it a scale out of 14? Right? Seems kind of arbitrary. But now you know where those numbers are coming from. They're coming from the Kw value that we have for water at 25 degrees Celsius. Okay, and so here is a question that is a pretty good kind of exemplar of the type of question you would see for this section of the course. And what I want you to do for this question is I want you to actually solve it in two different ways. I don't want you to just solve it in one way, but solve it using two different strategies. So pause the video, give that a try, and then see how you do. Question reads, in a New England state, the water on one lake was found to have a hydrogen or hydronium ion concentration of 3.2 times 10 to the negative 5 moles per liter. I want to know the pH, I want to know the pOH and of the water, and decide whether it's acidic or basic. And so let's see. So I'm going to go ahead and try out one way to solve this. I'm hoping you're able to come up with at least one method, but I'm going to show you two. So the first way that I might go about this is to say, well, let's look at what my givens are. And I'm not given a whole lot of information. I'm given that my hydrogen ion concentration which we're going to say is equivalent to our hydronium ion concentration, and that's 3.2 times 10 to the negative 5 moles per liter. So one way that we can use this is we can find the pH, and that's going to be equal, pardon me, to the negative log of my hydronium ion concentration of 3.2 times 10 to the negative 5. So let's see what that gives us. Approximately 4.5. That's what I'm getting for my pH. So already I can tell, that falls in the acidic range. So this is definitely a lake that has been acidified, probably, possibly by acid rain. So in the second part of this, what I'm going to do is I'm going to go ahead and I'm going to go show you the whole first way of doing it, and then I'm going to go and duplicate this slide and show you my other method. So now that I know this, the pH, finding the pOH is easy because, pH plus pOH is equal to 14. And so substituting in my 4.5 for my pH, I get that the pOH is equal to 9.5. So something interesting is happening here. Because my pOH is 9.5, that doesn't mean that it's a basic solution. The pH and pOH scales are actually reverse. So just as for pH, a low pH means it's acidic, and a high pH means a solution is alkaline. A high pOH value actually means that the solution is acidic as well. So they're sort of flipped that way. So that's my first way of doing this question. I'm going to show you a second way to do this. The second way that you can do this is to still, again, we really just have that hydronium ion concentration, don't we? So, my hydronium ion concentration is still the same, 3.2 times 10 to the negative 5 moles per liter. But in this case, I'm going to use kW. So kW is equal to my concentration of hydronium ion times that of my hydroxide. And the value for kW is 1.0 times 10 to the negative 14. I have 3.2 times 10 to the negative 5 times my hydroxide ion concentration. And, I would have found the pH probably directly here in the same way. So my pH is still going to be that 4.5. But to get my hydroxide ion concentration will allow me an alternate route to finding my pOH, aside from using that pH-pOH relationship. So I'm just going to go ahead and calculate that. So 1.0 times 10 to the power of 14 divided by 3.2 times 10 to the power of negative 5, I'm getting 3.1 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 moles per liter. And so let's just examine that for a minute and think about it rationally. This is, we've already decided the lake is acidic. And so we would expect our hydronium ion concentration to be larger than our hydroxide ion concentration. And it is, in fact, right, to the negative 10. So that's just, making us feel more confident in our answer there. So now that I have my hydroxide ion concentration, I can find the pOH by taking the negative log of my hydroxide ion concentration. And I have that value in my calculator. So going ahead and taking the log, I'm getting 9.5 as well. So just so you know, there are multiple strategies to solve questions like this. We have one last topic, and then I'm going to send you on your way. So the last topic is pKW. So, pH is equal to the negative log of our hydrogen ion concentration. pOH is equal to the negative log of our hydroxide ion concentration. So not shockingly, pH is equal to the negative log of kW. And it turns out that pKW is equal to 14 at 25 degrees Celsius. So that allows us actually to create another formula, which is that I know, first of all, that pH plus pOH is equal to 14. And I know that pKW is also equal to 14. So I know that 14 is equal to 14, and that allows me to say, well, then therefore pH plus pOH must be equal to pKW. And so that's another formula that may come in handy. pKW is equal to pH plus pOH. And that becomes more relevant when we start to talk about buffers, which we'll hopefully get to at the end of this unit. So there are some practice questions for you that I've assigned in our week plan. I would want to ensure that you do those questions, because when we return to class, we're going to be looking at Ka and Kb calculations involving weak acids and bases, and we're going to have to employ these types of calculations as part of a multi-step problem. So get really comfortable with these and knowing what to do when, so that when we return together, we will be able to sort of seamlessly move into those types, the Ka, Kb calculations.